Okay.
Yeah. All fine. We don't have Zoom presentation, so let's try and talk a bit about. Since we're on school, I think we can start anytime.
Yeah. I'm Jagan. I'm coming from India, and today I'm trying to explore about U-boot from scratch. The ideal goal of this presentation would be like I would present like what exactly the project community happens since from the start. So I would have many more slides. Please be patient. And myself, I'm Jagan. I'm mostly working for Linux and maintainer for U-boot and some few subsystems. And I even work for Build and Ecto. Here is the agenda of this talk. And the agenda is, I have described the agenda to start with the nutshell of U-boot and keep on adding one by one, and at the end I can detail explain what is the future plans and what are the mistakes we did while porting the hardware and everything. So the part one topic would be like a nutshell. In the nutshell, I can cover all the topics like a brief history and what exactly the U-boot means and what was the source code, how you build it from the sources, and how the U-boot has grown since from the birth to now, and what are the boot sequences and what are the ideal tools for U-boot right now using. Sorry? The history, it's a brief history, like it starts from Works and Tanks in about 10 years back, and now it's moved to Tom Rainey as a master maintainer, and now it's supporting all of the most of the architectures right now in our industry. And we have a recent release of last month, 2019.01. Sorry, it's a mistake. And we have a community like other open source community in the open source field, and we very much follow the same strategy. Like we release every 2 months, and out of the 2 months, first 2 weeks will be a merge window for the new features, and the rest of the period is for stabilization for fixes. So the same like any typical open source project, like maintainers will send the PRs and all the patches would be mainline list. And this happened to be since from the last release, and we have changed the release cycle to 3 months due to some request in the mailing list. Now it's been changed to 3 months and 3 weeks merge window. These are the hardwares we supported till now, and we have most of the hardware or processors in the industry we supported even the RISC-V in the recent U-boot versions. So we have many more developers and almost 1083 different boards in the mainline. So what exactly the bootloader? What exactly the U-boot means? Just say for example, it's in the nutshell, in the layman terminology, a bootloader can be a first firmware loader after boot ROM, and it will launch the Linux kernel or any applications. So that is a typical bootloader, and in the starting, when the project starts, U-boot resides in something like a bootloader phase. Like there are some architectures from NXP. They directly boot the U-boot from the boot ROM. So the initial stage of the U-boot is something like this phase. Since as it's been started, there was a information from the SOC loaders, like individual SOC vendors from like SOC like Xilinx or Freescale is coming with some kind of a SOC loader. They are not into open source at that time. Like that purely depends on a DDR configuration and along with some FPGA configuration. Those are not mainlined yet, or not been to any GPL license. So U-boot can taken care of this part in 2014 or somewhere. They come in with a solution called SPL. So the SOC loader can be upstream to U-boot. So the code of the SOC loader now part of the U-boot loader. So it can be terminated as SPL, like a secondary programmable loader. So in this stage, U-boot can enable to load all kind of SOCs with the different boot flows. And as U-boot has been growing further, there was an information like there was one more problem. It came up like SPL has some limitation since it's running from the SRAM. So SPL cannot fit all SOC related SRAM. So we came up with one more solution called as TPL. So if anybody wants less memory like 8K or less than 8K, they should use TPL. And the boot for is something like TPL and SPL and U-boot proper. So the year goes, U-boot become U-boot proper. The SOC loaders will become another stage bootloaders. This is normal build steps, how to build a U-boot, and all the three different stages, the bootloader source code is the same. The build system itself is changing a bit to build the respective stages. And this is a typical U-boot tree. We just follow the same as Linux, but with some kind of a commands for a user interface. And as I told you, like we have 3 stages of U-boot, and the build process starts with a normal scripting, and first it will boot the U-boot proper. Like in the left hand side there is 17 number. It starts with the U-boot proper, and the build step is moving towards SPL, and it will build the SPL images. And if the board support as a TPL, it will build the next TPL images. This is a typical U-boot sequence from the power on reset. There was a global descriptor for the entire U-boot source code, like what was the memory starting and memory ending. Is the frame buffer. All the global details will be initialized in the first in the initial stage, and it will look for initialization code like board underscore F, whether it is a SPL or TPL or U-boot proper. There are 2 different sequences. So if it is SPL or TPL, it will allocate some memory, and it will create some LE debug, and it will create DDR memory. So that the next stage bootloaders can use the same memory. But in case of this SPL, the SPL will run from the SRAM. Now on the SPL, you will find out whether it is a U-boot proper or SPL. If it's found as SPL, it will load a boot mode device. Like if I boot from the NAND or MMC, the respective NAND driver will load the respective images. So at the end, the SPL find out. There was one more stage called Falcon. I will describe it later. If it is a Falcon, it will boot the Linux directly, and if it is not Falcon, it will identify whether I need to go for GD stage and whether I need to go for ATF or OPTI. Say for example, U-boot proper, it will relocate the memory. Like it will since the SPL is starting running from the SRAM. While initializing DDR, it will reallocate it by itself to the top of the memory, so that the next image like Linux kernel can use the offset from the 32K. The U-boot proper sequence is something like it's a common sequence. That's why I have the init sequence underscore R, where you can what are the configurations you enabled in U-boot. All the configurations will be part of the sequence. And finally, if it is auto boot, it will boot Linux, or it can come with a U-boot shell. This is how the typical sequence. And we have a loading sources, any kind of a peripheral media source that can be useful here. And we have a simple debug printf, and we have config debug and LE debug. This is a LE debug information. It is very useful for porting the new hardware devices. These are typical tools that we are using in U-boot, like a patman for sending patches to the mailing list without concerning too much about what you are doing with a Git, normal Git. And we have buildman, like if you send a series of patches, the buildman will build all the series with respect to all the architectures. And there was one more concept called packaging multiple images. Like I told you, like 3 different stages of U-boot, like U-boot proper, TPL and SPL. Each stage will create a different images. So binman is useful to create one image from out of all 3. This is how typical binman look like. We need to specify the file output and some offsets, how it will load. This is a normal testing, we still use a Travis and test by trace normal like anything. And the next part is image boot. First is a legacy boot, like since from the U-boot starting, we have booting the Z image and U image fields. But there is like it has a fixed offset, and U-boot today have some U-boot format. So the problem with this image was like there is no flexibility, and there is a problem with indexing, and we cannot add some security features to the image. So there is no scope of the security edition. So we come up with a concept called fit, flatten U image, and just like a binman, it will have a DT structure by specifying all the images. So even in the images itself, we can even specify the hash. So the single image can create while redundant for each and every security. This is how it's fit loaded. And we can even expand the fit complexity, like we can even add multiple kernels and multiple DTVs and even the RAM disk. This is a special feature works mostly on the servers. And we can even add a bit file like FPGA, so that it could be part of the single image. And even we can add ATF for the ARM64. And we can add opti in if anyone want to run from the trust zone. And if any of the new image type, we can add it. And the fit extension is a verified boot, like how I can add fit image with the security. It's like a software security. We need to create a public and private keys, and the public key we need to put it on some trusted source, and the private keys could be part of the U-boot. So on the verification process, we can decompress the public key, and U-boot will verify the same thing. This is about in case of software security, we need to pump the public key to U-boot DTS, so that U-boot verification process will identify the public key and create the hash, and it will boot the proper hash if it is good or bad. And this is a real security, like I have tried in the IMS6. The same stage, like, but in case of U-boot DTS, I need to flash it into FUs. So during the verification process, I can compare the hash from the FUs, and I can U-boot can validate the image. This is a pure security from hardware point of view. And this is encryption. The main difference between the signed image versus encryption was like I need to create an image with a payload. Like if I have a U-boot image, once I created encryption, it cannot become a normal U-boot. It will have adding some hashes by encrypting the image. Since IMX comes with some kind of a OTP, during the decryption, it will get the OTP and it will validate the secure key. So the decryption process will allow in the U-boot like this. And the ATF stage. This is what normal U-boot flow, and we need to add ATF on top of the SPL. During the ARM64 boot flow, SPL will go to the ATF, and ATF will run some SIM code and to move back to the U-boot proper. And this is opti flow. Like I can add opti on top of SPL. So even there are two different kind of use cases. Even we can load opti after SPL and U-boot, and we can even load before loading to Linux, and we can load opti after U-boot proper. And this is opti use case in the ARM v8. Like I can load the SPL, ATF, and opti is normal, and even I can load by combining this in case of ARM v8. As I said, the Falcon boot, there was a concept called Falcon, where I can skip the U-boot completely, and I can boot the Linux from SPL. So this can be use case in case of boot time optimization or something. So the skipping doesn't mean that we need to skip the U-boot. We need to configure the Falcon in the first stage of U-boot. So you need to go dry run to the U-boot and create the Falcon, and the board next time will boot from the SPL to Linux. This is how we calculated boot time with respect to the Falcon. We ended up with half of the boot stage. And in 2017, we added something like a UFI support, since most of the x86 on ARM8 is coming with UFI. So you would come up with a UFI boot, like by specifying some kind of a UFI image. Like if you want to boot a BSD image or something, like you can boot it from there directly. There was a nice documentation about this if you want anyone like this. Yeah. And there was a boot ops, how we can pass the command line arguments from the U-boot. But the problem with the main boot ops, like it's board specific, we need to have a different kind of a language with respect to all the board configurations. So we come up with a concept called a distro boot, like a distribution boot by default. So it can be a default for all the distributions, like we cannot keep taking care of any board specific logic here. This is how U-boot XT Linux configs look like. And the next phase, like U-boot features. The first one is the kconfig, and I will describe all the features that are built from the scratch to now. So the first stage is the kconfig. at the U-boot starting point, we didn't use the kconfig, so it was a normal build steps. So in 2014, we ended up using the kconfig look like a Linux. But since we have 3 different stages, the kconfig can be categorized into 3 different config files, each config file for each stage. And we even add the FTT support, like you can reuse the same DTB for U-boot, since the same thing using from the Linux. So even you can specify the DTB and we can build the U-boot with DTB. This is like a normal DTB flow. And we have some specific use case for the DTB nodes. Like we always sync the DTBs from the Linux. If you want any DTBs or nodes properties with respect to U-boot, it could be part of some U-boot.dtsi file. This is how U-boot.dtsi file look like. And there was a requirement from the Linux. I wanted to change the DTB node while moving to Linux. Before I need to change something onto some property disable becomes, I need to do it like a enable or something. So I can do that in U-boot before going to Linux by using libfdt. So I can grab the node and I can go to the node and traverse to the node, and I can update the node if I wanted to update the node. The problem with this is like we need to traverse the entire tree, and there was a problem with the speed, and we need a rebuild the sources again. So we come up with a concept called live tree. Like instead of pointing to the offset, I can pointing to the pointer to the particular node. So I can directly go to the pointer to the node and I can update the DTB property. This is how live tree look like. This is sample code for how we can write a live tree. And we even add FDT overflows like overlays. Like there was a hats hardware on top of like Raspberry Pis. If the DTB on the particular board or a hat is not in the mainline, they are come up with a concept called overlays. So we even load the overlays by means of fit as well as manual. This is how you have a overlay DTB, and this is how we can load the overlay DTB. Like and the load address, I can specify the core DTB file and the next hash with the overlay DTB. So it can take the overlay and it will boot the Linux. This is how we can boot the normal overlay in the manual manner. The next concept I like a driver model, and this was introduced to make more features to the U-boot. I just keep track more. The initial stage of U-boot, we have a drivers like calling the function calls from the board. So they are not redundant. They are ended up with we cannot use the multiple controllers with the same flow. So we have a problem like direct function calls multiple. There is no scalability and difficult to maintain. So we ended up concept called driver model. The driver model look like this. Each device has a hardware device and along with the driver, and there is a U class. So say for example I have spy flash. I have a spy flash device from the DTB. And I have a driver, like if it is a controller driver, it could be a Jinx controller, and U class is the core. This is like a homogeneous with respect to the Linux device model. The Linux device model has something like we can have a device type, bus type, and there are various categories based on the device topology. But here all the devices are homogeneous. Look, like each and every device has a driver and U class. This is a simple modular, but there are some issue with SPL. If you want to use in SPL, you need to bear some size. The beauty of this driver model is a lazy initialization. Like see, in case of bootloader, you don't need to initialize everything like what Linux does. So I can do the lazy initialization. Whenever I need, I can initialize it in U-boot console. So this is a typical driver model we evolve. CPU driver models. Like if it is a CPU, I wanted to get the information, the U class underscore CPU. And if it is a DDR driver, I have U class underscore RAM. And if it is a shared memory, I have a driver concept called U class underscore SMEM. If it is MBox, I have a U class underscore MBox. And if it is a RTC, I have a U class underscore RTC. This is like how CPU driver model look like. And this is the power driver models. All the driver model will fashion something like this same. Like each and every driver, we have a U class drivers in with respect to controller drivers. And there are some core concept like a clock, reset, pin control. All this categorized into something like this. So we have a generic PI driver and even pin control. And we have peripherals like serial, UART, SPI flash, and GPIO and Ethernet. All the fit into the same category of the U-class flow. This is how typical U-boot driver model look like. I have written a driver like Zinc underscore QSPI. It's a controller driver, and this U-class driver is a core. This is how you can pass the operations. And we have one more layer like Linux. We have a generic block layer. So the U-class can be a parent to the other U-class. And it can be child to the other U-class. So here block is a U-class and it is a child for U-class underscore MMC. And we have U-class for block is SATA, SCSI and NVMe. This is how we can interact with U-classes. And this is the U-boot USB U-class framework. We even handle peripherals and everything. And we have, since I told you like if you use FDT, we can have a restriction for the size. So you can skip the FDT by concept called off underscore platform data. This is something like a legacy Linux platform device. Like I don't want to use a device tree, but I can use driver tree node by using this device installation. This is how we can upgrade the U-boot firmware. There are variety ways you can use it. We can use a device firmware and you can use a fast boot, even UMS. And if you want to port the new hardware, we need some kind of prerequisites like setting up the size, and we need to know what serial you are using, and you can use this. This is how we can port the new hardware. We can concentrate on the respective config files as well as with DTS files. There was a nice presentation on this, in detail presentation in the ELC 2017. If anyone wants, you can refer. And this is how U-boot look like with the 3-stage bootloaders. First it starts TPL and written from the boot ROM. It will start from the Linux and the MMC, SPL, and it will again go to the MMC and it will start to U-boot proper. This is how the typical future plans. If anyone wanted to participate in these areas, you can easily. And this is conclusion. And thank you. Any questions?
Any question?
I have a question about x86 support.
Yeah.
You would be used as a loader in the bare metal and virtual machines.
Yeah, even we have x86 boards, Mara board, and yeah, we have enough x86. Even we have a ACPA support in x86.
So only if there is USB, right?
Yes.
You can also load U-boot as a BIOS in QEMU. And use it as a BIOS instead.
Then standard to define when I want to have put in multiple device device, where mit bei den Werkzeug oder
Sorry, I didn't get you.
Sorry?
I didn't get your question.
When I have to fit in with multiple device device.
Okay, you need to specify the device tree from where you want to boot. Like I told you in the FDT overlay, right? You need to specify the core device tree by and the hash, and you can specify whatever device you want to boot.
Okay. But that's not standard.
It's up to you. You can write a standard in the boot configuration.
Okay.
Thanks.
No more questions?
Yeah.
Can you explain a little bit more about the upcoming features?
Sorry.
Can you explain a little bit more on the upcoming features?
The upcoming features would be like we are in a stage of removing all the legacy drivers, like moving towards driver model. So that can be a future plan I can see, because since it was started, driver model has been started almost 3 years back. We have not enough moving towards the driver model. So we already place the margins like milestones for each and every driver subsystem to merge. Otherwise, respective board will be removed from the main line. So our initial goal, right, the starting phase 1 goal would be move all the driver models.
Go ahead.
Are there any plans to remove all these custom include files that are still found in the tree and are still
Yes,
config
yes.
and header files directly?
That is also one more plan. I just described on the on the to-do.
Yeah.
Yes, K-config migration.
Yeah.
The configs which
It's
are
very annoying each time.
yeah, the configs which are not
Change the config and then
Yeah.
everything breaks.
For that you need to refer the config underscore whitelist. The configs which are not in the K-config, they are being listed in that config file.
Any more questions? Okay, thanks.
Thank you.